What's up, guys? This is 3.6 continued. We have one last concept in this section called log differentiation. It's exactly what it sounds like. We're going to use logarithms to change the form and then differentiate. So let's see what I'm talking about. Well, first we need to recall these log rules. So do you remember these log rules from back in the day? Well, first, the natural log of a product is the sum of the logs. The natural log of a quotient is the difference of two logs. And if you have something to a power that you're taking the log of, you can pull that constant out front, that exponent out front. And so notice what that allows us to do. That means that if I have a log that looks like this and I want to differentiate it, I can first separate it into smaller logs to make it easier. If I have something that looks like this and I'd like to take the derivative, I could first break it up into two smaller pieces and then differentiate. If I have something to a power, I can pull that constant out front, and then this might be easier to differentiate. So what does that mean? That means if I have something that looks like this, what I can do is I can use logarithmic differentiation, which means first I'm going to take the natural log of this side and the natural log of this side. And I can do that because if these two inputs are equal, then when I plug them into the log function, the outputs must be equal because natural log is a function. So for every input, we have at most one output, right? So equal inputs means equal outputs, right? Okay. But now watch what happens. Over here on the left, it just stays kind of boring, but on the right, I can first view it as the natural log of a quotient, where I have something divided by something else. So that means I can write it as the natural log of the first thing minus the natural log of the second thing, right? So what it really is it's the natural log of x to the fifth minus the natural log of something a little bit bigger, and maybe I do this. So it's actually the natural log of 1 minus 10x times the square root of x squared plus 2. Got it? So if you have a difference, a natural log of a difference, the natural log of a quotient is the difference of two logs. Well, now notice what we have here. This is just a product of two things. And I know that the natural log of a product is the sum of the logs. So notice what we're going to do. We keep this over here. We don't lose track of it. But then here I have minus, and I'm going to now replace, if I can help focus your attention, I'm now going to replace this, maybe green this time, this times this with the natural log of two things added together. So this is going to end up being the natural log of 1 minus 10x plus the natural log of the square root of x squared plus 2, right? So notice that I had to subtract a big piece means that I'm subtracting all of this, so that when I break it up, I have to have these parentheses here so that I subtract this small piece and subtract this small piece. Okay? Awesome. So now what I'm going to do is remind you that that square root is just the same as all of that stuff raised to the, yes, very good, 1/2 power. So that's 1/2, right? And now what can I do? I have the natural log of stuff to a power. I can now bring this constant out front. So just take your Apple Pencil and copy all this and then hit paste. If you don't have an iPad, I recommend asking Santa for one. When you pull this down, you get a 1/2 out there in front now. So this is gone, and there's now a 1/2 out front. But then also notice this negative is here, it distributes to this and makes this negative, and it distributes to that and makes that negative. So this first one's going to become negative, and this second one is going to become negative. So notice what we've done. Now I've got something that I'm ready to take the derivative of. So all of this was just algebra. And now I'm ready to do my calculus. Okay? And what I'm going to do is I'm going to take the derivative with respect to x of both sides. So I'm going to take the derivative with respect to x of this side and the derivative with respect to x of this whole side over here. So remember, all this is getting differentiated, so I'm going to put it in here. Again, this is a lot of extra detail, but I'm really making sure that you are following along at home, right? So this is just the natural log of y. Okay? So notice that the derivative of the natural log of y, what we're going to do is we are going to assume that y is a function of x. So when I do, the natural log of y is 1 over y.
But Dad.
Yes.
What does y equal?
We don't know. It is a variable, kiddo.
And what does x equal? It depends on what the letters equal.
I know. We'll have to think more about that next time.
Yeah.
So you get your PJs on, kid? So y prime over y, or I guess I could write it as, yes.
And my high ability teacher, Miss Marsh, said that x equals 8 or 9, and y equals like sometimes 10 or 9.
Oh, very cool. I didn't know that. Awesome. Cool. I got to finish this real quick, okay?
Okay.
Thank you.
See you later. I got my clothes on.
Awesome. Thanks.
I'm fully naked except for my
Whoa, yikes. Okay, share time. Okay. So the now I'm going to take the derivative of, notice I didn't mean to have this here. So it's just the natural log of this stuff. Excuse me. So now I'm going to take the derivative of this. Well, what is the derivative of natural log of stuff? It is 1 over stuff times the derivative of that stuff. But the derivative of x to the 5th is 5x to the 4th. Right? But then again, this was, oh, I did the wrong piece. So let me make sure that this is a 1/2 out front. We had already changed this. We know that. So this is a minus, and this is a minus 1/2 over there on the end. So that's that. Just so that we can see what's happening. That derivative is that.
I would recommend actually saying the name of the thing and not just saying that, because
Okay.
I might not know what you're talking about.
Okay, thank you, baby. So the natural log of 1 minus 10x, when I take its derivative, is 1 over 1 minus 10x times the derivative of 1 minus 10x, which is negative 10.
You're good at this.
Thanks. And then I have minus 1/2, and I'm going to take the derivative of the natural log of stuff. And so the derivative of the natural log of x squared plus 2 is 1 over x squared plus 2 times the derivative of x squared plus 2, which is 2x. And there you go. Pretty awesome. So let me now take all of this and let me hit copy. Let me get a new page. And when I hit paste, whoa, can I see it? When I hit paste, now I'm going to simplify. And what I have is y prime over y is equal to, well, do you see that x to the 4th and x to the 5th kind of cancel out and leave me with 5 over x? And this minus and minus here, this minus and minus give me a plus. And this is plus 10 over 1 minus 10x. This 2 and this 2 cancel out. And that leaves me with minus x over x squared plus 2, right? But then notice I have y prime over y. So to get rid of that y, I just multiply both sides by y. And so I get y times all of the stuff on the right-hand side. So our answer would be that the derivative is y times all of this stuff. But notice what I can do. If I just leave it that way, it might seem like my derivative is a function of x and y, but it's not, because my original function back over here was this big ugly thing. So what I can do is I can copy it, and I can replace all of y with this. So I just replace y with what it's equal to, and I get that my derivative is equal to all this stuff times everything that we found here. Hit copy and paste. And there you go. So that is the derivative of the original function. So we're now done. I wouldn't want to simplify any of that. Please don't try. We would hurt ourselves. But notice what we did. First thing, we did a whole bunch of algebra, and we took the log. And then we did implicit differentiation on both sides. That's why it's called log differentiation. The derivative of this, we have y prime over y, yes? And that's always going to happen when you take a natural log of y and take its derivative. You're always going to get y prime over y. Okay? Awesome. So then the last step in implicit is always going to be, when you have y prime over y, the last step is always going to be to multiply both sides by y. And then if you want to replace that y with the original. Okay? So we just have a couple more examples. So that is one case where it's nice to use logarithmic differentiation. Here's an example where you must use logarithmic differentiation. So that was example 1. Let's now do example 2. So if this is example 2, what if I had y is equal to x to the x? So this is a function raised to a function. So notice this is not a function to a constant. It's not something like x squared. It is a function to a function. So this is a function raised to a functional power. And so that means you must use logarithmic differentiation. You must. Okay? And let me show you why. Because you have y is equal to x to the x. What I can do is take the natural log of both sides, right? And when you do, a lot of math and science is about form. I can change the form, and I can pull down that exponent. So I can take this exponent and pull it out front, and that's going to give you x times the natural log of x. On the left-hand side, I'm still going to have natural log of y. And so now I have something that's much better to take the derivative of. So now I use implicit differentiation, take the derivative of this side and the derivative of this side. So over here, I'm going to take the derivative of that. Over here, take the derivative of that. Okay? So notice I had to do I had to do algebra to get me here. And now I'm actually going to do the calculus.
Good.
All right. So what is the derivative of natural log of y? Well, we said every time it's going to be 1 over y times y prime. And the way that you write that is usually y prime over y. That's what this is always going to be on that left-hand side from experience. But then right here, notice if I ask myself, what is the form of this thing right here? Is that candy cane good?
Yeah.
This form is stuff times stuff. So we're going to do the first times the derivative of the second plus the second times the derivative of the first. So the derivative of natural log of x is 1 over x. The derivative of x is 1. So what we get is that y prime over y is equal to 1 plus ln x. But then, remember, the last step is always to multiply both sides by y. And so I get this as my derivative. But the way it's written now, it looks like y prime is a function of x and y. But guess what? It's not. So what we end up doing is replacing y with its original function. Its original function was x to the x. So the way that we're going to end up writing it is the derivative of y is x to the x times 1 plus ln x. Okay, and that means I just have one example left that I'd like to do, similar to what we just did. Let's do example
3.
And so what we're going to do is we're going to say y is equal to 1 minus 3 to the x raised to the cosine. So notice this is a function to a function. I cannot use the power rule, and like bring this down and raise it to the cosine minus 1. That makes no sense. Since this is a function raised to a function, I must use logarithmic differentiation. So that means
if you do that, if you do that, and I said not to do, then it would not make any sense. And you go,
exactly.
that doesn't equal that.
I know.
That equals that.
I know, right? And so now that I have this, I've taken the log, that's the algebra, and so now I'm ready to do the differentiation, and I take the derivative of this side and the derivative of this side. Oh, I don't do that yet, do I? Oh, see, Eleanor, we weren't focusing. Well, now the whole reason why we took the log was so that we could change the form, because a lot of math and science is about form. So I'm going to take this exponent and pull it out front. So I now have cosine times the natural log of 1 minus 3x. Over here I have natural log of y. Now I can take the derivative. So don't take the derivative too early. The whole reason we took the log was to pull down that exponent.
And you didn't do that mistake on purpose.
Yes, good call. I did or didn't?
Didn't.
Oh, thank you for letting them know that. So if I take the derivative with respect to x of this side and the derivative with respect to x of this side, we're now just going to have to be careful, yes?
Yeah.
So on the left, what is it always equal to? It's always equal to y prime over y. Because the derivative of the natural log is 1 over y times the derivative of the inside, which is y prime. So that's why we get this always for log differentiation. But then you ask yourself, what's the form of this thing on the right? Do you see that it's something times something else? So that means we're going to do the product rule. So I'm going to say first times the derivative of the second. Let me move this over so I have more room. Move this over here. First or second, what? Plus the second times the derivative of the first.
I'm going to go wash my hands because my hands are pretty red from that.
Please do that. And so what we have here is y prime over y. Yep, cosine of x. What's the derivative of the natural log of stuff? I guess I could say that the form of this thing is the natural log of stuff. So its derivative is 1 over stuff times the derivative of the inside, which would be negative 3. And then over here I have this, and then times the natural log of cosine, times the derivative of cosine, which is negative sine. And make sure to put parentheses, okay? So to clean it up just a little bit, we have y prime over y is equal to negative 3 cosine over 1 minus 3x. I'm almost done, kid. Minus sine of the natural log of 1 minus 3x. So notice how close that is to being done. Cool. Yeah, could I leave it that way? I don't want to actually pull anything out, do I? I could pull a negative out of both if I wanted to. So here's what I'm going to do. I'm just going to rewrite it like so. Let me make it a little bit smaller for the audience. So resize.
Smash.
Thank you.
Yeah.
Okay, thank you. And so now, remember what we always do is the last step on these things. This is a y on the bottom. I don't want that y on the bottom, so I multiply this side by y, and I multiply all this by y. These cancel. And I get that y prime is equal to y times all of this stuff. Control copy. Yeah? So it's going to be times all of this stuff. But what was y equal to? Don't forget y was equal to, in the original function, it was equal to 1 minus 3x raised to the cosine of x. So that means our derivative is equal to the original thing, 1 minus 3x to the cosine multiplied by all this stuff. And that's what our derivative is. So great work. The other thing I really wanted to hit home, and this is in the typed out version of the notes, the derivative of a constant to a constant is 0. The derivative of a variable to a constant is the power rule. The derivative of a constant to the x is actually a to the x natural log a. Remember we spoke about that. And then now you know how to do the derivative of x to the x. Stop, please. Thank you. Is x to the x times 1 plus the natural log of x. Thanks, sweetheart. She was really enjoying her juice box there for a second. So this is a constant to a constant. It's root of 0. If you have a function to a constant, it's the power rule. If you have a constant to a function, that's this a to the x type thing, yeah? And then if you have a function to a function, you do not have to memorize this rule, but we just know it's log differentiation, yeah? So you should be able to see the difference between these. Great work. There is homework. I'd like you to work in your normal groups, and I will talk to you soon. You want to say bye?